Thank you so much. Thank you, everyone, and thank you, Gaetano, for the introduction. I'm Iacopo Spalletti. I've been working with Python and Django for almost 15 years, mostly doing web applications, and then an active contributor of the Python community, especially in the Django ecosystem, and I work at Nefila. So, async programming. Async programming is a pattern with the goal to reduce the impact of blocking I/O calls on our applications. I will drop a lot of code on you. I'm sorry. I hope you will be able to follow me easier. In practice, in async code, when we execute a blocking call, we give back the control to the other calls in the queue without requiring us an explicit handling like we would do with threads. Basically, using a cooperative multitasking approach directly implemented by the async library of choice, which provides us a higher level API to make our life easier. This is a useful resource in our toolbox, especially in Python, where the GIL has a few limits and on parallelization, and multiprocessing and multi-threading libraries are not super developer friendly. The biggest result that you want to achieve in a synchronous application with a lot of I/O calls is to make a better use of our CPU to handling more connection. I'm talking about network applications, of course, as we can pause the execution of a request that is waiting for I/O and then serve new connections and improving the concurrency, which is a number of requests that you can handle in a span of time. But sometimes it's easier to make confusion between concurrency and performance. Concurrency doesn't mean that you get better performance on a single request. Actually, we have a little overhead. But what we want to achieve with either concurrency is to be able to serve more requests with the same infrastructure and make a better usage of our resources. And just a silly example to explain the concept. When a waiter serves a new client at a restaurant, they basically execute three tasks. They take an order, they wait for the dish to be prepared, and they serve the plates. A single waiter can only take one order at a time, but once the order has been passed to the kitchen, the waiter must wait for the dish to be ready before serving it. If we are using synchronous programming, our waiter is going to wait out of the kitchen, waiting for the dish to be prepared, and the other clients are left unattended. In asynchronous programming, and in real restaurants actually, the waiting time is used to take other orders, serve dishes that are already being prepared, and so the single client have a much lower waiting time. When you have a microservice architecture, this is an old actually representation of some Amazon API, Amazon Bookstore API. When you have a microservice architecture, we have a lot of messages going through all these microservices, and each message has latency, overhead, and waiting time, basically. If these microservices are written using synchronous programming, you will waste a lot of time waiting, and obviously, and a lot of time means a lot of money. If you use asynchronous programming, each microservice can switch to another request while the message they have sent is completed, and so the flow can go on. An important consequence of improved concurrency is that, speaking about the usual HTTP request-response cycle, we can break this cycle, basically, and we can pause our blocked call and wait for something to happen, so for the message to return, enabling basically event-based of functioning, of connection in our code. So our code can be paused and kept waiting until something happens that thaws it, and react to the events coming registered basically for our code, like in a pub/sub architecture, WebSocket, message queues, and of course in web we are probably more used to talk about WebSockets when we establish a persistent connection between the client and the server, and messages go through as they are needed. We are not going to talk about WebSockets today. I gave a talk at DjangoCon Europe about Django channels, which is an asynchronous framework for Django, and I'll provide a link at the end of the talk. In Python, asynchronous programming is a relatively newcomer within the standard library. There has existed for a long time frameworks like Tornado and Twisted, but they were fully fledged frameworks, not basic library like async-IO. In 3.5 we have async-IO in the standard library, so the barrier of entry is lower, basically, for the standard programmer. And then more libraries has started, like Trio and other, but we are going to talk about basically async-IO, not that other libraries work very differently. So let's extend a bit our example. So how do we define an asynchronous function? First of all, asynchronous functions are called coroutine, because they behave differently behind the curtain than plain functions, and are defined by using this async keyword, which has been introduced in Python 3.5. And one important thing to notice is that only coroutine can execute other coroutines. So you have to plan the whole stack of calls to make sure that you have a coroutine when you want to execute another coroutine. And if you call a coroutine like this, you will not get the code inside this coroutine executed. You will get back an object, which is the coroutine object, which is useful if you want to, I don't know, schedule or launch multiple coroutines in parallel, etc. In other languages, this would be called a promise. If you want to actually execute the code within it, use the await keyword, which means we want to wait for the coroutine to be executed and for the coroutine to return something before proceeding with the calling coroutine. One important thing to notice is that you can't execute a coroutine in the synchronous flow of Python. You need an event loop, which is basically something within async-IO which handles the coroutines and all the events of exactly the events that happens in the synchronous world. You just execute basically this. This is the preferred way to create an event loop. Just call run with the first coroutine, which actually the entry point basically of your application. Writing microservices with bare bone async-IO is not the most time-effective way to write a microservice, so we use frameworks. And specifically, we worked with FastAPI, which is a nice framework, recent framework, of course. We like it because it's type hinting based, so you have very compact and very Pythonic code you work with, and it has a very nice, very tight integration with OpenAPI, so you have for free, relatively free, documentation and client generation, etc. And contrary to other SGI frameworks, has some batteries included, like serialization, authentication, etc. These are all provided by FastAPI, so it's a very effective way to work with it. At the base of FastAPI, actually you have Starlet, which is a low-level async framework for Python, and Pydantic, which is the data validation library, entirely type hinting based, again, like FastAPI. So it's basically an opinionated version of Starlet plus some battery. But why not Django? I've been using Django for 12 years, so why not using it for implementing async services? After all, async views has been introduced in Django 3.1. Django 4.1 will introduce async ORM, which will make a huge difference, and class-based asynchronous views. It's reliable, it's proven, we know exactly how it works, etc. But especially for very focused microservices, you won't need all the features and code and footprint of Django. And worse yet, Django REST framework does not have yet an asynchronous implementation or support for asynchronous views, so you have to implement a lot of things by yourself. And of course, trying something new is always exciting, so why not doing that? This is a very basic example of a FastAPI application. If you know Flask, you can probably guess 99% of what's happening here, because the concepts behind are almost the same. We will quickly go through this simple example, then we will see a more, slightly more complex one. The first thing we do is instantiating a FastAPI application, which is actually an SGI application. But what's SGI? SGI is a standard protocol for asynchronous network application in Python. It's basically what is in the synchronous world, what WSGI is for the synchronous, for the synchronous world. In practice, we have an SGI server which starts the event loop and execute our application within this event loop. It listens for incoming connection and pass the connection to our application. So it's basically our gateway to the external network. One of the important concepts of SGI is that everything is an app. So our app equals FastAPI is an application, is an SGI application, but also routers and middlewares we will see later are actually application, and you can pipeline all these applications together to have a more complex workflow without breaking, without having corner cases or special handling of each. You can just pipeline these applications, and if you have a router, whenever you have a router, you can have a middleware and mix and match all these things, because they are all applications. Of course, we want this app to do something, so we connect, we define in a routing, so we find the HTTP verb and the path, and its arguments, of course, in this case, a path argument. And we attach our coroutine. In this case, as a coroutine, you can define also synchronous function as well as path operator. This is the way FastAPI calls it. Within this view, you can do whatever you want. This is just some kind of business logic which gets some data from somewhere. In this case, this is a coroutine, so I must await it. But basically, you can do whatever you want here. And to return the data, you just return, for example, in this example, I return a dictionary, but you can return a response object. You have a lot of options here. And on top of this, without doing much, you have a very basic documentation of what you have done. For a more complete implementation, you can have a look at this repository. And we won't go through all this code because it will take too much time, but this is a very simple implementation derived from a real production application which provides some insights. The first step is to have an SGI server. In this case, we used Uvicorn, which is, I'd say, the most used SGI server around, as some similarity with Unicorn, can control protocols, performance, and whatever you want. A nice thing is that as Uvicorn is Python itself, you can basically create a dunder main.py in your main package, instantiate the Uvicorn and run it, and provide the entry point applications. So basically the path, the dotted path to the FastAPI application, and then you can run this way. One nice thing is that with this way, you can have all the configuration, the Uvicorn and the application configuration in the same object, and you have a very much more coherent way to handle the configuration of both the components. Now we are creating our FastAPI application. The first thing we want is obviously having a way to configure it, and so we have this settings object, which is provided by FastAPI. You basically define with type hinting all your variables, which can be environment variables. You have a type, you can define default arguments and whatever. If you want, you can use a .env file to configure them. And this is basically a standard feature. One of the batteries provided by FastAPI. Then you instantiate the application. You can provide a lot of arguments basically to configure application metadata, OpenAPI interface, and whatever. In this case, I just provide some random project name. And as I told before, we have middleware, which are SGI applications that basically sits between before and after the execution of the main flow execution, and can check whatever comes from the request or check what the response has generated and reach the response, complete control of what's happening in before and after the application logic has run. And they are basically a coroutine. For example, here you provide a callback to the next application in the call stack. For example, you can register the time the request has been initiated. Here there is all the application logic that runs here. The response is generated. You take the process time, you add some other random process time, and you return the response. So you can control whatever happens before and after the response has been generated. So you can add, for example, for authentication and stuff like this. And last, we add a routing, of course. You have basically two ways to handle routing in FastAPI. You can attach route directly to app, like we did in the first example. But actually, the more efficient way is to have to add basically a router to instantiate a router application. This is again is an SGI application in itself, and so you can include routers which come from your own code or from external code without passing in some way your main application. And this is the way we switch to to sub application with this sample project. Here you instantiate this router. You can have multiple routers to attach different path operator. And so we basically define that on this verb, on this path, there is, we attach this path and this verb to this router, and we can add multiple arguments to this get function call. But we will see them later. As I said, I could have done something like this: import the main application within my this specific module, and I could have appended the route to the main application, but this will lead, of course, to the more complex code, and it will leak a lot of your abstraction into the main application instead of being able to handle the routing within each package. And yes, so we have here, we have the function, well, actually the path operator definition. Here you have the arguments, which can be defined again using type hinting. So this is an integer, list of string, this is a string. And you can further configure them or specify them by using these classes. In this case, are all query attributes, but you can define that, I don't know, here is a path, is part of the path, or is it part of the body of the request by using this class provided by FastAPI. And you can provide some arguments to this, like the description for the documentation, or I don't know, the default value, or some validation, additional functions, and so configure exactly what kind of arguments you would want. A very a very useful feature, but also, let's say, a pillar of FastAPI is that it works by using dependency injection. Your path operator, a lot of the things you are going to use in your path operator, like database access or, I don't know, Redis or whatever, are passed as dependency injection. Dependency injection is when you pass to a function an object or another function that the main function is going to need to do what they need. In this case, we pass the request, which is, of course, something that is going to be needed in a network environment, and you may pass something like settings. And actually you can define whatever dependency you want by using this depends keyword. I'm running a bit late. And then whenever you have defined what's the input, you have your business logic here. This is a very basic call to an Elasticsearch, to the Elasticsearch client. One thing I want to stress is that at some point you may have to run some blocking, some synchronous call within your application, and you must be aware that asynchronous is not a silver bullet that will solve all your problems. The more deep you have coroutines call instead of synchronous call, the better results you will have in terms of concurrency, because of course if I have this one which calls a synchronous function here which has a blocking call, I will basically have no advantages because all the code will be executed synchronously. So I will basically have a synchronous call. In this case, we use the synchronous Elasticsearch client just to make sure that to have the maximum benefits of using a synchronous call. And then we have the response. Again, this is just a dictionary, but we can provide a schema that this dictionary must respect. And the schema is defined by using Pydantic models, which are these kind of objects. These are a bit simplified, but they're basically all here. So you can define the fields or the attributes of the objects by using scalar types or more complex type like this. Result is a list of book, and book itself is a complex object which has a list of author, list of tags, and etc., etc. And without going much into details, these are Pydantic models. So whatever you want, whatever you can do in Pydantic, you can do that here. If you come from Django REST framework, be aware that Pydantic is not similar to Django REST framework serializers. It's very powerful when it comes to data validation, but when it comes to data serialization, you can't have much flexibility. You don't have anything like the serializer method field you have in Django REST framework. So don't try. I tried, and we actually do something in Pydantic to handle the data, but don't do it. Just prepare the data for the schema in the business logic. Testing, of course, you want to test the business logic, not much you want to rely on business logic testing, but sometimes it's useful just to also test the views. And you can test the views synchronously by using the test client provided by FastAPI. You just initialize with the app and reverse the real URL with this function, or you can do this asynchronously with HTTPX, which is the asynchronous equivalent of requests. And once you have initialized them with this way, basically the rest of the test is usual normal test code. Asynchronous programming can be tricky, a bit tricky, especially when you are debugging, because in this case it's very simple, but in real world cases you have things that happens and you don't know why, or when it comes the message you see. But under some workload, it provides great benefits. So it's something that definitely you want to explore. We have frameworks like FastAPI that makes our life definitely easier, and you can focus more on the business logic than handling whatever happens in the asynchronous world. So it's a wrap. Thank you. And if you want to know more about channels, this is linked to my Django Con Europe talk. I really need to have to update this because something has changed, but the concepts are the same. We are hiring, so if you want to have more information, go to this page or talk to me. I'm around in the conference for the whole weekend. These are my contacts. If you want to contact me online or offline. Any question?
Iacopo.
Thank you.
We have a bunch of questions. Why did you say that FastAPI is opinionated?
Because by providing you things like serialization, authentication, middlewares, etc., it has its own way to do things. With Starlet, you have a lower level way to handle asynchronous not programming, but asynchronous network applications. So you are more free to do whatever you want. With FastAPI, you have to do a few things. You have to do the FastAPI way. It's not something that you can. I mean, you basically can't. You must use Pydantic, for example, for handling data validation. You can choose another data validation library and things like this. Not as opinionated as Django, but still a bit opinionated.
Okay. What ORM do you use with FastAPI?
Sorry?
What ORM do you use with FastAPI?
In our case, we don't. In the microservices we have, we are building. We don't use a database, so we don't use any ORM.
Okay. In a sync approach, what happens if the service has been called dies for some reasons?
In asynchronous world,
Yes.
If it dies, it dies. You have to handle the exceptions, like having a timeout or something. So that thing doesn't change really.
Okay.
I mean, if the service you are calling dies, this will anyway generate a message, and your coroutine will be resumed, and instead of having the data you expect, you will have an exception. So you are going to handle it, but that's the same as synchronous one.
Does the async keyword create processes or threads? And how is the GIL involved in the asynchronous execution?
Basically, async.io, I'm not a super expert of the async.io internal, so take this, my answer with a grain of salt. Async.io works with threads, so you can't escape the GIL. It's not it's not a way to break the GIL. You are going to have it, but if you have microservice, you will have very compact processes. So your goal is to spawn a lot of processes, and this is a way, of course, to not encounter problem with the GIL.
Okay. How do you debug async.io code? Especially, how do you follow the trace of a single request?
with a lot of sweats, basically. Yeah, you have to. That's the hard part of asynchronous programming. Sometimes you have messages and you don't know where they come from. Writing tests, which involves a lot of asynchronous synchronous code, can be tricky, and especially in another project we actually use channels, not FastAPI, so we have the ORM, and you have very much aware of what's executed in the synchronous context and what is executed in the asynchronous context, so basically have a good debugger. I have a very good experience with PyCharm integrated debugger, which provides you, when you set a breakpoint, you have all the threads that are being executed, and this provides you some insight of what's happening inside your code. But it's a bit tricky. There is no real solution. I mean, a single technique that helps you in doing this.
Okay. Does the async keyword create processes or threads?
No,
another one. Can the client know the progress of the async request?
It depends. You can. I mean, you must handle yourself. For example, the synchronous request can have a callback and send a message during the execution. You can send a message to something else, which will react and send back the information to the client. So yes, you can. It's not something that you can do within the single coroutine, but in the code that you are talking, in the code you are writing, you must handle the steps yourself. I mean, if it's a single request that you are sending and you expect a response, there is no way to have a progress of this. But if it's an operation with multiple steps, at each step you can send a message to other part of your code, and this part of your code can bring back the information to the client. So you can. It's not something that any asynchronous framework provides out of the box, but it provides you the tools to handle this.
Okay, 30 seconds. Why use async approach instead of event-driven approaches such as Celery and RabbitMQ? What kind of benefits it can give?
Well, there are actually things like Celery and RabbitMQ are very specific to some kind of workloads. I mean, if you have to run something that resembles a batch job, I mean, something that you put an inputs, runs for indefinite time, and then you may want to have an output out of it. It's okay. Of course, you must. Probably they're better suited than pure async-IO, pure asynchronous programming. But if you want very small, I mean, if the goal is make a request and return a response, or maybe collect response from many different requests and send the payload in the same HTTP request cycle, it's better suited. If you want, I don't know if you can implement WebSockets with Celery. You can't by itself because Celery doesn't know anything about the network. But I mean, you can send messages from Celery to something that communicates via WebSocket to your client. But Celery or RabbitMQ are basically made with batch operations in mind. With asynchronous programming, especially with FastAPI, you just want to have you are still working with the concept of request and response in mind. You have seen here in the middleware coming. Well, where's the middleware? Here. The middleware knows about request and response. So FastAPI especially is made for the to handle HTTP world. And in this case, you don't want to. Your goal is not to have something that runs for indefinite time and somehow eventually will return a result. You will want to return the result immediately to the user, but you want to handle multiple requests using the same resources. So you don't want something that you fire and forget, which is basically the approach of Celery. You want something that you can control, but you want something that when a blocking call happens, will not block the whole stack of calls. I don't know if I answered the question, because they are very different. And okay,
Okay.
Come to me later.
Thank you, Jacopo. Great talk.